Hello everyone. Sorry for this technical glitch. My app got frozen. I need to restart it. I hope everyone has a good relaxing spring break and welcome back. And of course, tonight we have our project 2 submission. I see that 1/3 of the class already have submitted the project. Uh, Hopefully others are on track for the project submission. Uh, any question before we start tonight? No question at all. Okay, let's see. So, as I mentioned in the last day before the spring break, that we are switching gears towards more abstract discussion of the computer architecture topics. And this one is not any exception of that. This lecture 13, computer performance measurement, this is also some abstract concept of how we can measure performance, predict performance, and design a processor for performance improvement. So our target is for the processor performance improvement, runtime improvement, in a sense. And to do that, we of course need to know how do we measure that improvement, right? So there are two concepts where we have gone through this lecture already, just to make sure on the important points that you need to be very clear about these two concepts of response time versus the throughput. If you think computer as a like a service agent and you are the client of that service agent, in that sense, response time is more like from your side, from the client side, that you are given a problem to the computer and then how much time it takes to get back the result to you. So that's the response time. Whereas throughput is from the service agent perspective, like it is more from the processor perspective that given a time period like 5 minute, 10-minute, hour, whatever is your benchmark criteria is, given that period, how many jobs are done. So that's the measurement from the server side or service agent side. That is the throughput, whereas the response time is more from the client side, like when someone is starting a program, how long it will take to finish that program. So that's the key concept there. And performance is classical definition wise, it is 1 over the time, right? It's basically your execution time, 1 over. If you take that quantity, that's the performance point. Um, Second thing is that like there are you will see or already have seen that there are different approximation levels of these performance related computation. Like one approximation is that like average clocks per instruction, right? So we take and we run through many programs, many like standard program, benchmark program we call it, and then kind of take an average that how many cycles it takes per instruction. Then we can grossly measure that if my program is going to execute n number of instruction, then how many cycle it needs, then multiply by with the time period of the clock, we get an approximate estimation of how long it's going to take in that target processor. And then we from there we can drill it down to several other detailed parameters, detailed CPI. Maybe we can classify them like, okay, these are my classical R type instruction, these are my I type instruction, these are my J type instruction. And we can measure the CPI per classes of this instruction. Then we, in that case, if we know what is the mix of these different types of instruction in my target program, then it will be a better estimate of the performance of the execution time on the target processor. But the key point here, if you want to notice, we are talking about an estimate, right? It's more like a prediction of future that computer architect takes as a tool to change the design of their processor with some target in their mind, with some target value in their mind in terms of performance, that hey, if I change my architecture in this way, I can improve the performance probably maybe 30%. And if it is valuable in the market space, let's go for it, something like that. However, once the processor is designed and it's implemented and being fabricated on a real silicon device, after that, we measure the real performance. Like we run the benchmark program, which is the standard program established in the industry, and every processor company has access to that program, run them and publish their result. That hey, this is the integer benchmark. This is maybe an classical web server benchmark. This is an supercomputing benchmark, so on and so forth. There are different classes of benchmark program, but all these things are targeted towards standardizing this performance measurement, that you run this common set of programs and then measure what is your total execution time, and give and see if your theoretical prediction actually matches with this number, your expectation. And based on these studies, then architect develop their future model of prediction for their next generation of processors. And while our target is basically to make efficient processor every year or every quarter, depending on the release cycle of this industry, of the specific industry. Maybe Intel has one release cycle versus AMD has another release cycle, so on and so forth. Main target is to optimize this performance, right? And in that respect, Amdahl's law is very important in that sense, that which part of the processor should we target even to optimize. And Amdahl's law, and through that equation, you'll get a sense of which of the module you need to target to, so that if you like improve the performance of that module, it will impact the overall system performance more than if you target a very tiny module from performance perspective. By the way, this Amdahl's law is not just for the hardware or architecture, it is also for your I would say for any system, even in the software systems, when we in the industry try to optimize performance either for the time, execution time, or the memory footprint, we basically analyze our software as well. Like let's say we divide the software in different modules and analyze the memory performance or runtime performance and see which modules take how much part in it, and we target the biggest module, like biggest chunk, which takes more time. If we can optimize that, it will have most impact in overall system. So that's the basic idea of the Amdahl's law, and you guys need to be sure that you understand that part as well. Question? No question? Okay, all right. So we can do some problem in group. Let me share my whiteboard and I will put two problems there. Maybe we'll take 20 minutes in group to discuss among yourself to come up with a solution. Then we'll discuss the solution together. All right, so here are the problems. Did I share already? No, okay, share. All right, so I'll give you two problems related to this one. One is goes like this. And by the way, these two problems are related with each other. Let me give you the second problem as well. Okay, let me explain these problems to you. The first one says that it's basically performance comparison between two systems, Px and Py. Okay, X and Y, two systems. X is running on a clock of 1 gigahertz, and another system Y, let's say one is from Intel, other is from AMD. Let's say they're running on 1.2 gigahertz of clock. Both of these systems support four type of instruction, like their classes in A, B, C, D, just some generic class. This is a table which shows the CPI, clock per instruction, for each of these class on the X, system X and system Y. Obviously, they are different. Like system Y is perform better with the instruction set type A and B and C and D as well. But for instruction C, it actually needs more time. Okay, so the CPU X, system X is optimized on better do performance on these classes, C classes of instruction. All right, now to compare this performance between these two systems, one benchmark program is used, which has a mix of 25% of A, 25% of B, 30% of type C, and 20% of type D. And given that, you need to compute the performance gain, or at least comparison between Y and X, and tell us that which is slower, which is faster, and by how much. Then the second problem is related to the first one, that this compiler team of system X of Q1, this question one, realized that all type of instruction A used in that benchmark program can be converted to type C instruction using two of them. Okay, so one instruction compiler team can spit out instead of instructions from set A, two of the instruction from set C. Okay, and so it will actually increase number of instruction anyway in the target compiled program. Now, if they change their compiler to implement this type A replacement, what would be the new performance gain? So the idea for this system X is that, hey, we are trailing behind on A with respect to Y, but if we can replace some of these with C, where we actually do better, maybe we can beat system Y. So that's the target. So here you see in this example, your software team is involved. There is nothing to do with the hardware side, no design change, nothing else. It is a compiler team who builds a compiler. That team is targeted to kind of compensate performance on which came up with this new architecture for that specific benchmark program. Question before we go into the breakout room? Okay, all right. Okay, I'm opening the breakout room for 20 minutes to do this in a group, these two problems. And there are groups with one people I see. Your study buddies are not here. So I will reassign you guys, okay, once I open the room. All right, here it go. Or maybe I can reassign actually right now. Just hold on. Okay. Okay, I think at least groups has at least two people. I'm opening the room for all of you. All right. I hope you guys have fun solving this problem. How about study group 5? Did you guys do that? Group 5, Guillermo, Wang, Nguyen, Antoine, group of those people?
Yeah, I think we did it, but I don't know if it's correct or not.
Yeah, that's fine. Like, why don't you just share problem number 1?
Okay. How can I share my screen?
Oh, yeah. Let me just, open up the share. Yeah, please do.
All right. Okay. So this is how we did it. For px, that's gonna be 25% times 4 instruction for type A. Likewise, we have that for type B, type C, type D, and then the sum of that gonna be 2.4. We do the same. We did the same thing for py, and we got 2.3.
Okay.
For conclusion, we got py over px equal 0.958.
Mm-hmm.
So I think that's y is 4.2% faster than x.
Um, okay. I think what you missed um, is to have that consideration for the clock. See, the X is running on 1 gigahertz clock, whereas system Y is running on 1.2 gigahertz clock. So
Oh, okay.
in that factor as well onto D. So your 1.21, that is pretty close to the answer. Your approach is correct. You only need to bring in those frequency factor into
I
this
got it.
calculation. It's 1.257, like 25%, about 26% better uh, than that one.
All right.
Thank you very much, Nigman. This is a good approach. Let me explain this to other as well. Others, if you have any question, tell me or tell Nigman. Otherwise, I'll explain. Okay, let me share my whiteboard with you guys. Okay, here, share. Okay, now you see that we have been given already this mix of the instruction, right? So if we say that, hey, there are n number of instruction in total, what we can safely say is this is like 0.25 0.25 n, right? This is 25%. And then the other one is also 25% B. C is 30%. So this is like 0.3 and 30%. And D is 20%, right? So this many instructions are there. We are just dividing them into different classes. So 0.2. All right, now this many instruction. So this is my number of instruction per class, okay? And that means I can compute CPI for, number of clock cycle, number of cycle for X like this, right? It's, this is like 0.25, this guy, okay. This is 0.25 multiplied by n multiplied by 4, right? 4 is coming from here. This is clock per instruction is 4. So that is that. And then for the next one, it is 0.25 multiplied by n multiplied by 2, because the CPI is 2. Similarly, we can extend the whole thing towards like others, 0.3, sorry, uh, 0.3 multiplied by n, that is number of instruction multiplied by CPI, that many clock. for the D 0.2 multiplied by N multiplied by 3, that is the CPI. That is for the system X. And similarly, we can do for the number of clock cycle for Y, which would be same computation, but change the CPI. Take it from this table for the Y. So CPI for Y multiplied N multiplied by 1.25 multiplied by N multiplied by 3, and oh, sorry, my bad. This is 0.3 and this is 0.2 multiplied by N multiplied by 2. Now, if you sum it up, like total, like sum it up, then it will become like about 2.44 N, that many cycle, and for Y, it will become like 2.3 N. Now, this many cycles needed, and given the frequency of X, I should take a right notation there. Let's see. If X, frequency of X, given 1 gigahertz, so that means time period for X is 1 by Fx, which is about 1 nanosecond. And similarly, frequency for Y is 1.2 gigahertz. That means time period for Y is 1 by 1.2 gigahertz, which is about approximately 0.83 nanosecond. If you compute that, it will become like this. That means my execution time for X is this guy, 2.4 N multiplied by 1 nanosecond, and execution time for Y is 2.3 N multiplied by 0.83 nanosecond. That means my performance Y by performance X is execution time X by execution time Y, which is 2.4 N, and this one is 2.3 N multiplied by 0.83. This N gone, and if you calculate that, it becomes about 1.257. So Niguan, you see that this is what we get with respect to when we add the frequency component in our calculation. I believe you did till here. What you need to do, multiply it with the clock period of the systems. All right.
All right, thank you.
Question?
At 1.252 after doing that math.
1.252. Okay.
1.57. It's 1.25217.
217. Yeah, approximately. Okay. Let me see. Let me just bring out the calculator. Maybe I'm wrong in that calculation. So we're talking about we're talking about 2.3, the denominator, right? 2.3 multiplied by 0.83, which is 1.1. So this is like, this one is 1.909. This is 2.4. So 2.4 by 1.909. Hey, this is 1.2572027, something like this. Did I make a mistake?
No, I have 2.4 divided by 2.3 times 0.8333 repeating.
Oh, okay. So you basically, I did round that part. 1 by 1.2 gigahertz, which comes about 0.83333 recurring. So I just took 0.83. But anyway, it's kind of on 25% amount. The like performance calculation uh, may not be exact. Like if it is within that 25%, 26%, that's all basically architect looks for. It doesn't go much into the decimal digits. But your answer is correct too if you are just taking a 0.8333. Yeah. All right. Other question? Okay. How about study group 13 on the problem 2? Study group 13 is Harrison, Abhijit, Gargi.
Oh, hey, Professor.
Yes, Abhijit.
Okay, we got something. I think we're on the right track for sure. We didn't write it out necessarily. We just talked about it. So number 2, it's very similar. It just says this type A instruction can be implemented using 2 C instructions. So so 1 A instruction is 2 C instructions. So we just since A instruction takes 4, the CPI of X for A is 4, but we're using 2 C's instead. So we're gonna have, for 1A, we have 2 C's. So I used the CPI of X for instruction A. The new CPI was 2, and we just basically used that number 2. Everything else was the same, and it dropped, and it changed the overall result, the performance gain.
Did you get your final result?
I actually made a mistake in the previous part with the computation, so my answer is not going to be correct.
Okay, that's fine. I think your approach is good. Let me show that for others in the class, and maybe you can tally up with your solution. All right?
Okay.
So thank you, Abhijit. Let me share again my whiteboard. Okay. All right. Now you see what the software team did is make this into 2 of C. So it increased the number of instruction, but it actually avoided this high number of CPI. So your C calculation for Y is remains same. What the other team did is drop this guy, right? And then bring in 2C and 0.25N. Like this is with 2C plus on top of this guy, right? So it added up onto this. So your calculation, CPI calculation would become something like, for the first one, group A, it is being replaced by C, 0.25N, multiplied by 2 for the C, and CPI of C is 1. Plus, it remains, other things remain the same. So if you do that calculation now, it becomes like about 1.9 n number of cycle. Instead of 2.4 cycle, they reduce down to 1.9 n number of cycle. So your Py by Px is now Ex by Ey. Ey will be same. It will be like 1.909 n, and this guy will become 1.9 n, which is basically about 0.995, little bit faster. Now the system X is little bit faster than Y on this benchmark program. Now you see that this like software can do a lot of impact on the business side, in terms like if some processor comes out to be slower on a benchmark, software team make a tweak. this compiler team can make a tweak possibly, and make the product competitive. Question? Okay, let's take a little bit break, like 5 minutes-ish. 8:25 we'll be back. Okay, let's be back, and it's a pop quiz time. So let me, okay, go to, that is pop quiz 6 has been published. So if you go click there, and if you're ready to enter the password, say yes to this poll. Okay, 21 of 32 so far said yes. 27, 28, 4 more to go. 29, 30. I'll wait a couple of more seconds. 31, one more person to go. All right, let me share the password. Here it goes. Here you go. Okay, I think for most of you, time is up. Let's see if I can bring some quiz statistics on this. And also, let me start recording. Okay. So let's see what happens here on the quiz side. So here is the statistics. Average score 67%, below pass mark. High score with 100%, and this is your distributions looks like. This is the easier topic. Basically, you guys need to do better on these quizzes. Speaking of that, let me share one more things with you, which is a little bit of concerning as well for me. Not much though. This is your distribution about the midterm. I'm done with the midterm points, and your median and average, if you see, it is not even passing grade. It's 67.5 on the median side. Max is 94.75. That's good. And this is your average distribution looks like. Most, like 9 people are on 875 to 80 points, and then some people on 80 to 85 points. These are the most people went there. 85 to 90 and 90 to 95 is very few people. Four of you guys. Pass marking is on this 70 grade, so this part is more like your passing grade part, right? Which is about what, 6, 10, 19, 27, 30, 31. So maybe I think 52. About 60% of the class got pass, and then we have 4 people. I think these people who didn't show up in the exam, they have given up already, or maybe planning for a late drop. So I won't be worried about them. What is worrisome is your quiz 2 outcome, right? Quiz 2, if you see, the pass rate has dropped from 94 to 80%. I don't know what happens there. It is the same set of question. You have 2 atoms, right? One you see who failed or didn't answer correctly, then you go back, study, and they redo the same exam, same set of question. I'm not sure why this has gone down. And similarly with the B minus or better from 91 to 63. This is very alarming. Please make sure to do better as a whole in the class in quiz 3 and quiz 4. If your study groups bodies are struggling with points, please discuss this problem with among yourself and see what can be done, right? And tutorial wise, I have in the announcement and I have the link for the tutorial request for 147. If you need, please go through them, like go to them and ask for tutorial tutors for this subject. Now, overall, so far, till midterm distribution, 1/3 of the class is A minus or better. That's good. And remember, this is without the bonus points. Bonus points will come in. Once it comes in, this curve will shift towards the right. So more people will step onto the passing marks and the A minus or better marks. So this is good. This is not good. D plus or less, which is the failing marks, 25%, 1/4 of the class. Hopefully, once these 2 projects, like 400 points comes in, things will get better. Question. I will post the midterm grade after this class. And tonight is the project submission, project 2 submission. Don't forget on this part. And project 3, I think, is published. Please work on that. And is there any other thing this week you need to be worried about? Let me see. Assignment wise, is there any upcoming? Project 2 is upcoming. I think that's it. Project 2 is done tonight. Project 3 is posted. Okay. Okay, all right. I think this is all. And by the way, like now I have started this, open up this get level lab. Please go through those videos of the lab. It is very much needed for your project 3, and each of these lab give you the task for the project 3. So project 3 doesn't have a milestone like project 2 had, but each of this lab 11 to lab 17, those tasks given in those videos are basically towards your project. All right, please make sure you follow through them, you implement them, and start on the project 3 right away. Question? All right.